All right, so we started to talk about primality tests, pseudoprimes, Carmichael numbers. So let's just review that a tiny bit. So the Euler-Ferma Theorem says that if you have a positive integer m and an integer a that's relatively prime to m, then a to the phi of m is congruent to 1 mod m. And if m equal p is prime, then if a is not divisible by p, phi of p is p minus 1, a to the p minus 1 is congruent to 1 mod p. So this gives a primality test. So let n be a positive integer and let b be an integer such that b and n are relatively prime. If b to the n minus 1 is not congruent to 1 mod n, then n is not prime. Because if n were prime and b was an integer not divisible by p, this would be b to the p minus 1, not 1 mod p. It's not possible. So this is a primality test. And we say that n is a pseudo prime to base b if b and n are relatively prime and b to the n minus 1 is congruent to 1 mod p, mod n. So this is a pseudo prime. And being a pseudo prime doesn't mean you're a prime. It doesn't mean you're not a prime. It means that for some number b, n satisfies the test for primality. So it's a necessary condition, but it's not a sufficient condition for a number to be a prime. And we saw a couple of examples of pseudo primes to some base b that were in fact not primes. And the question is it always possible to distinguish a prime from a composite number by one of these pseudo prime tests, one of these primality tests? And a counterexample to that statement would be something we call a Carmichael number. So a Carmichael number is a composite number. So it's not prime. A composite number n such that b to the n minus 1 is congruent to 1 mod n for all b that are relatively prime to n. So a Carmichael number is an integer, a positive integer, that passes every one of these primality tests, but it still is not a prime. And it's a very important fact in number theory that Carmichael numbers do exist. And the smallest example is constructed in the text, and it is 561. So let n equal 561. And this number is divisible by 11. This is 11 times 51, and 51 factors into 3 times 17. So 561 is definitely composite. It's 11 times 3 times 17. And minus 1 is 561 minus 1 is 560. Which of course is composite. If you factor it as 10 times 56, 10 times 7 times 8, eight is 2 cubed, so this is 2 to the 4th times 5 to the 7th. That's n minus 1. And I claim that if, no, just 1 second, let me shut that off. Yeah, so I claim that if B is any number relatively prime to 561, then B to the 560 is congruent to 1 mod 561. Right? If I can prove this for all such B, then this number 561 passes every one of these primality tests, but it's not a prime, so it is a composite number. So suppose B is an integer which is relatively prime to 561. 561 is divisible by 3, so B is certainly relatively prime to 3. 3 is a prime. 3 squared is congruent to 1. Mod 3. So B to the B squared to what's half of 560? 280, I think. B squared to the 280 is it's still 1. It's just 1 to the power 280. So if B is relatively prime to 561, it's relatively prime to 3. So B squared is 1 mod 3. So maybe I should have written this in the following way. B to the 560 is B squared to the 280. That's congruent to 1 to the 280, which is 1 mod 3. Also, if B is prime to 561, then B is prime to 11. Which means B to the 10th is congruent to 1 mod 11, which means B to the 560 is B to the 10 to the 56, because 10 times 56 is 560. This is 1 to the 560. This is 1 mod 11. And finally, if B is relatively prime to 561, then B is relatively prime to 17. It's not divisible by 17, which means B to the 16 is congruent to 1 mod 17. This is all just Fermat's theorem, which means B to the 560 is 16 times 35. This is B to the 16 to the 35th, which is 1 to the 35th, which is 1 mod 17. So what we've just shown is that if B is any integer relatively prime to 561, then B to the 560 is congruent to 1 mod 3, mod 11, and mod 17. So 3, 11, and 17 divide B to the 560 minus 1, and these are relatively prime moduli. So b to the 560 is congruent to 1 modulo 3 times 11 times 17, which is just 561. So this is a very beautiful example of a Carmichael number. It's a number that is not prime. It's a composite number, but it passes every primality test of the type we've just been considering. Okay. Any questions about this? Okay. So the very last topic I want to discuss is an extremely important practical application of number theory to cryptography, which is the study of creating and using secret codes. So you have a message you want to send to someone, which is usually called the plain text. And this is the sender. And someone is going to receive the message. And read it. But of course, someone can intercept the transmission and read the message. So if your message is, we'll have a surprise attack against the enemy at 6 tomorrow morning, it's no surprise if the enemy knows you're going to attack at 6 in the morning. So you don't want that message, if it's intercepted, to be read by the enemy. So you convert your plain text into some code, which is called the ciphertext. Cipher is another name for a code. So this process of taking your plain text, let's call it P, and converting it to the ciphertext T, this is called encryption. And the receiver gets the message, the ciphertext, and he converts it into the original text that he wants to read, and this is called decryption. And if the enemy intercepts and reads the transmission, hopefully the enemy doesn't know how to decipher the text. He just gets the ciphertext, but he can't read it. So the message is secure. Okay. And how do you keep your message secure? I mean, this comes up constantly today, right? You go to Amazon.com and you want to buy something, and you use your credit card to pay for it. So your credit card number, this is you, gets sent to Amazon. And they charge your credit card and send you back your product. But of course, you can't just send your credit card number, because then the enemy, whoever that is, intercepts the transmission, steals your credit card number and uses it. That's not very good. So you need to encrypt. So your credit card number, that's the plain text. You need to convert that to some ciphertext C, which is what you send, and then Amazon decrypts it, deciphers it. Now, how do you know how to encrypt it, or how does your computer know how to encrypt it? Well, if they told you the method, if the encryption method was the same as the decryption method, that is, if knowing how to encode your message also teaches you how to decode your message, then it's not very secure. So what's a simple example of an encryption method? So every message, I want to buy a book. I want to buy Shakespeare's collected works. So what you would do, actually, I mean, it's kind of trivial. You convert your message in words into a number. So you assign a number to every letter or whatever. That's not very secret. But basically, your plain text always becomes a positive integer. And everyone knows how you get from the integer back to the words. There's nothing secret about that. So here's one encryption method. Choose a prime P, much bigger than your plain text message P, and choose E, relatively prime to P. And how do you get your ciphertext? Take P, raise it to the power E, and reduce that modulo your prime. So your plain text P, if you raise it to the power E and reduce it mod P, that gives you the ciphertext. And this is some jarbled up thing. You can't just look at C and figure out what P was. You can't do that. It's too hard. So your method of encryption to go from your plain text P to your ciphertext C is to take P to the power E modulo some large prime. And how do you decipher this? Well, choose D such that ED is congruent to 1. Mod P. E is relatively prime to P, so you can use the Euclidean algorithm to solve this congruence. You know this congruence has a unique solution mod P. You can find D. And how do you decipher? You take your ciphertext C, raise it to the power D. Sorry. I want to choose D such that ED is congruent to D modulo P minus 1. And here I choose my encryption number E such that E is relatively prime to P minus 1. So everyone knows how you are creating your secret code. You give the sender the prime P and this number E relatively prime to P minus 1, and you encrypt by taking P and raising it to the power E and reducing it mod C. And because E is relatively prime to P minus 1, you can solve the congruence ED congruent to 1 mod P minus 1. That means ED is 1 plus P minus 1 times some number K. So if I take C and raise it to the power D, that's P to the E raised to the power D. That's P to the ED. But ED is 1 plus P minus 1 to the K. This is capital P. And P to the P minus 1 is 1. This is just congruent to P mod little prime little p. So this is one encryption method. Take your plain text, that's some positive integer. Choose a large prime P, much bigger than capital P. and choose an integer e relatively prime to p minus 1, and you encrypt your message by taking p to the power e. Now, if you know the prime p and the number e, you can use anything like the Euclidean algorithm to solve the congruence ed congruent to 1 mod p minus 1, or you can find a number d such that ed is 1 plus p minus 1 times k. Right? Because e and p minus 1 are relatively prime, you can always solve this equation. So c to the d is p to the ed. That's 1 plus p minus 1k. Capital P to the p minus 1 is 1. So this is just p. So the trouble with this encryption method is, if you tell someone how to encrypt the message, and if you're Amazon and you're doing a lot of business, everyone has to be able to encrypt their credit card numbers. But once you know the encryption method, you also know the decryption method. So this is not a useful code. So what we would like to have, a code or a crypto system where knowing how to encode a message does not let you know how to decrypt or decode the message. And some very clever people came up with such a crypto system, which is called a public key crypto system, or a secret, well, right, public key crypto system. So here's what you do. Choose two large primes, P and Q. And what you do with them is multiply them. So M is the product of these two primes. So phi of M, that's phi of PQ. So by the multiplicativity, P and Q are distinct primes. This is phi of P times phi of Q. This is P minus 1 times Q minus 1. And choose an integer E such that E and phi of M, this is phi of M, are relatively prime. So how do you encrypt? So given a plain text, an integer P, let's see. So here's what you do. You publish, you tell the world E and M. Right? You choose two large primes P. You don't tell anyone what they are. You multiply them together, PQ, and you call that M. You know P and Q, but you tell the world not what P and Q are, you tell the world what M is. And you choose an integer E that's relatively prime to phi of M, and you let C be P to the E. P is congruent, C is congruent to P to the power E mod M. So this is your encryption method, right? P is some number, capital P, less than M. And C, just take the least positive residue, C is also between 0 and M. So you start with your plain text and you tell everybody in the world, if you want to send me a secret message, take your message P, raise it to the power E, I'm telling you what E is, and reduce it mod M, and I'm telling you what M is. Okay? Now again, how do you decrypt? Because E is relatively prime to phi of M, choose D such that D well, let me put it like this. Choose a D such that E times D is congruent to 1 mod phi of M. So you know what M is, you know what P and Q are. If you know P and Q, you know phi of M. And I can solve this congruence. And just as before, if I take the ciphertext C and raise it to the power D, this is P to the ED. This is P to the 1 plus some multiple of phi of M, which is congruent to P mod M. Because P to the phi of M is congruent to 1 mod M. But I claim that no one except you can break this system. You see, what do you need to know to break the system? You need to know phi of M. So this is the data that we're given. So the world knows E and M. The world knows M is a product of just 2 primes, P and Q. You can decipher if you know phi of M. Which is P minus 1 times Q minus 1. And you know phi of M if you know P and Q. And what do you know about P and Q? You know M is equal to P times Q. So to find P and Q, just factor M, right? You're given the number M. You're told even that it's a product of 2 primes. Just factor M and you'll find the 2 primes. So why is this hard? It's essentially impossible to solve because factoring is essentially impossible to do. Now you say, well, it's easy to factor. If I give you a number like 91, it's a product of 2 primes. It's, I think, 7 times 13. I just factored 91. Right? If I give you 1,000,000 and factor it, that's 10 to the 6th. That's 2 to the 6th times 5 to the 6th. I just factored it. If I give you a bigger number, you can say, well, I use Maple. If I write I factor the number M, this gives me the factorization. The problem is that by hand or maple, you can only factor numbers that are relatively small. If M has, let's say, 10,000 digits, so it's easy to write down a number with 10,000 digits, no computer can factor it. Why not? No one knows why not. Has never been done. A huge amount of money has been invested in trying to do it, but it's never been done. And it's a major unsolved problem in mathematics, whether in fact there's any efficient algorithm to factor a number. You say, well, try every possible divisor, just divide by every number. But the fastest supercomputer might take millions of years before it can finish that trial division process. It's not in a sufficiently efficient way. So factoring an integer, this is a very simple problem, right? You can give this to kids in elementary school. You know, you can say, here's the number 12, factor it. Or here's the number 15, factor it. And you can do that. But when you have big numbers, even if you're told in advance, this number is not a prime, but it's only a product of two primes, find the two primes, there's no one, there's no computer, there's no intelligence agency anywhere in the world, as far as we know, that can do this. And the difficulty of factoring a number makes this code, which is called the Rsa Crypto System, after three guys at MIT a long time ago, Ravesh, Shamir, and Adelson, who came up with this and patented it and made a lot of money. Because basically all of internet commerce, international banking, the most secure military codes, government codes, are all based on this idea that you can use the difficulty of factoring an integer to make what is, as far as we know, an unbreakable code.
Professor.
Yes.
So from what I heard, with the new quantum computers, they are saying that possibly very soon they will be able to factor large
Right.
numbers.
So the problem is that quantum computers don't exist.
They're working on them, yeah.
Of course they're working. And so it is known in theory that a quantum computer could factor an integer into primes. It could solve this problem. And a huge amount of money goes into the development of quantum computers, and they're still basically, they still can't do anything. That is, the problems they can solve are on the order of, you know, factor the number 6. If you were to tell a computer to factor the number 91, I suspect that there's no quantum computer at the moment that could even approach that problem. So there is something in theory called a quantum computer, and people are trying, engineers, and a huge amount of money. Every federal agency everywhere in the world, every computer company everywhere in the world, Microsoft, Apple, Amazon, anyone you can name is spending a lot of money to look into trying to construct a quantum computer. But the difficulties of the engineering problems are hard. So yes, in principle, if there were a quantum computer, then you could break this code. And if that happens, there are other codes that we have that that we could use instead. So it's not like cryptography would come to an end if people learn how to factor numbers and break this code. There are plenty of other codes which are much harder to break. But as with many other things, there's no reason to change your encoding system now or in the immediate future, because these codes are still very secure. And the cost of changing your encryption is, hundreds of billions of dollars for a large company. So yes, if there were a quantum computer, this code would no longer be secure. But there's no quantum computer, so it doesn't matter. No one can predict the future. So it may be someone somewhere, or some large industrial group somewhere that has $100 billion or so to investigate these things, might come up with a slightly more efficient quantum computer. But it's like, we have nuclear power plants that use fission. The energy released from breaking a uranium or a plutonium atom, and the heat is used to generate electricity very efficiently. A more efficient way would be to use what's called fusion. If you take two hydrogen atoms and you force them together, you create a helium atom and you release even more energy. And a fusion reactor to produce electricity would be much cheaper, more efficient, and cleaner, because there's no uranium waste left over, radioactive waste left over. And people have been trying since the hydrogen bomb was invented about 70 years ago to create a fusion reactor. And it's never been done. I mean, people still work on it, and there's still a lot of money that goes into it. So there are lots of engineering problems, which if you could solve them would be very useful to the world. But like fusion, creating a quantum computer, you can't say it's not going to be done. It probably will be done eventually, but you don't know whether eventually means 10 years or 100 years. For the moment, and actually you can check if you look, for example, on the Amazon website, there's always something which you click and it tells you what encryption is being used. And it's always some version of this Rsa Crypto System based on the difficulty of factoring an integer into a product of primes. Any questions about any of this? It's really extremely interesting, and it's worth studying just to know about, because this RSA system's been around for quite a long time now, and people are very confident that it is unbreakable by current technology. There's no proof it's unbreakable. There's no proof that you can't factor a number efficiently. It just hasn't been done. And what happens is, what gives a crypto system credibility is the fact that a lot of organizations, individuals, governments have tried to break it and failed. So when that's the case, you tend to believe it. But it is, in mathematics, in number theory, a major unsolved problem to know if, in fact, there is an efficient classical algorithm to factor integers. No one knows that. And if you can come up with one, you will become very rich and very famous. And your life will probably be in danger, because various pernicious actors will try to kidnap you and have you reveal the secret. There used to be a show on television which where there were two brothers. One was an FBI agent and the other was a mathematician. And the FBI agent would always go to his brother and his brother would always figure out some mathematical way to solve the crime. And in one episode, someone gets murdered, and they figure out he was murdered because someone thought he had figured out how to factor numbers. And if they had his method, they could break into the international banking system and steal, billions, if not trillions of dollars. So at one point, at least, this curious bit of mathematics made primetime television, made it into primetime television. Anyway, we're done, actually. So there was a syllabus, and we've covered the syllabus. The last topics were pseudo primes and Carmichael numbers and the Rsa Crypto System. So I will send out a review sheet for the final. I'll send it out today, actually, I think. And we'll go over it on Monday. And the final exam, according to the Lehman College and CUNY final exam schedule, is, when is it? Monday, December 20th, 8:30 in the morning, not at 9 o'clock. Final exams for 9 o'clock classes at Lehman always start at 8:30. So 8:30 to 10:30 in about 2 weeks. And I will have lots of office hours. I mean, after we go over the review sheet next Monday, I will have lots of office hours over the following week. So if you have questions, you can always log on and ask me. Okay.
Perfect, Professor. Thank you.
Anything else? I mean, we're really done. So
when you gonna post the review for the final?
Today.
Today? Perfect. Good.
Yeah.
Plenty of time to study.
I mean, it'll have a lot of questions just because, it's just like good practice, but, it's a review sheet. It's not homework. You don't have to turn it in. So it's just to give you some additional problems to study from. But the review sheet, it doesn't restrict the final. I mean, it's always the case. The final covers everything in the course, and but a lot of the problems on the final certainly will be like problems on the review sheet, but not necessarily everything. Okay. All right, if there's nothing else, then we will quit for the morning.
Have a good day, Professor. Take
Thank
care.
you.
Thank you.
Maybe it's supposed to snow today, so don't get caught in the snow if you can avoid it, I guess.
I'm gonna sleep.
Okay, bye all.
Bye. Take care, Professor.